I'm going to talk about MEG and what gives rise to the MEG signal. So MEG refers to the method of measuring magnetic fields outside of the head, produced by neuronal activity in the brain. So what sort of neuronal activity gives rise to these magnetic fields? Neurons communicate via action potentials, which are electrochemical impulses that travel down the axon and trigger postsynaptic potentials in the dendrites of the postsynaptic neuron. Action potentials have a very short lifespan of only a few milliseconds, where postsynaptic potentials have a longer lifespans of tens of milliseconds. This means that over time, the net current of the postsynaptic potentials will add up, and it's this temporal summation which gives rise to the measurable magnetic fields outside of the brain, outside of the head. Of course, you also need a large number of neurons in order to produce large enough net currents for them to be measurable outside of the head. We model these currents within the brain as current dipoles, which is a simple model of a moving charge. We model the head, the medium through which these currents travel and which these magnetic fields propagate as a spherical volume conductor. So volume conductor refers to some conductive medium, and conductive means that currents can travel through this medium. And because the head is sort of spherical and it's conductive, both the skin, the skull, and the brain itself is conductive. That's how we model it as a spherical volume conductor. Now, certain conditions are necessary for the sources of these currents within the spherical volume conductor for them to produce external magnetic fields. And the first thing is the orientation of the source. So we have radial sources which are aligned on any line that goes through the center to the surface of the sphere, and then we have tangential sources which would be perpendicular to a radial source. Radial sources don't produce magnetic fields because in a current dipole you have the primary current, which is the direction of the current, and then you have these volume currents which go back. And these two currents, or the primary current and the volume currents, they cancel out the magnetic effects of these moving currents, and thus there is no magnetic field produced. Tangential sources, because in a spherical volume conductor, that is, tangential sources, because of the asymmetry between the surface of the sphere and the inner side of the sphere, these volume currents are also asymmetrical, and therefore we see measurable magnetic fields outside of the spherical volume conductor. Furthermore, we have the alignment of the sources relative to each other. So in a open field, you will have, let's say, the dendrites of these neurons, they would be aligned like horizontally. This will produce a magnetic field, but if you would have them like radially aligned, also what is called a closed field in a circle, this would not produce a magnetic field because it would cancel each other out. Also, if the sources are just randomly put together, they would cancel each other out mostly. And then finally, we see these conditions met in the cortical surface, where we have these pyramidal neurons with long dendrites that are spatially aligned in this certain way that we need in order to measure with the MEG. And in order to get a good signal-to-noise ratio, we need to average across many trials, because this lowers the noise and this raises the signal, because we would expect the signal to be the constant thing across these trials. And this averaging is called the evoked response.